This inconvenient, but well, I guess that will be fine also to have this lecture today here. So let's start with the last lecture of this mini course from Professor Martin Bojowald. And well, today is going to be related with quantum gravity. So please, Martin, let's start.
Yeah, thank you. Yeah, I'll introduce more about quantum gravity. And well, not really that much, but just to indicate where some of the modifications come from. And a little bit of an analogy with matter systems, or something discrete, which you can compare with the condensed matter systems. And then also a few more details about cosmology and some effective equations that have been used for cosmological applications. And then finally, there will be some connections, but maybe this point will be a little bit abrupt here, the change. There have been similar approximations in Heisenberg's spin chain, which wasn't obvious, but we noticed this recently, and that's another example where they know the full theory, the Heisenberg spin chain. And people have done numerical calculations to compare these approximations. They don't call it mini superspaces, but in some cases it's pretty much the same thing. So I'll talk about this, and that's also another example of these canonical effective methods, in this case computing ground state energies and configurations. And then finally quantum chemistry, maybe more surprising. I won't really talk about chemistry, but the mathematical methods are very similar. The actual example will be a ton of them. So a look on gravity first. So the problem here on the first few slides will be constructing a kinematical Hilbert space for the full theory. So and the kinematical Hilbert space, as opposed to physical, comes up when we have constraints. So we first try to just define operators for the original configurations or fields which are not constrained at this point. And then at some point we follow Dirac's procedure and quantize the constraints to operators and try to solve them. But if we have a field theory, then even the first step, just writing down the kinematic Hilbert space, is not trivial for various reasons. In particular, if it should be coordinate independent or background independent. So the main questions are addressed here, although it's all classical, but we need well-defined Poisson brackets before we can do a canonical quantization. And just for a scalar field, the Poisson brackets that we usually use are not well-defined. There's a delta function instead of zeros or ones, which would have for finitely many variables. And we can't quantize this directly. There's no delta function operator on a Hilbert space. What we usually do here for a scalar field that's pretty easy, it's called smearing. So we integrate the fields just over space with two arbitrary functions a and b here for the field and its momentum. And then we can work out this Poisson bracket, which is no longer infinite on the right-hand side. So instead of using just points x and y to parameterize the fields or eventually operators, we use the functions a and b. So if they are smooth, then everything, or even just continuous, everything is well-defined. Now the problem, it's slightly more difficult if we don't use fields on flat space, which I assumed here. So these are just coordinate integrations, but fields on curved space, because that requires an integration measure for coordinate invariant expressions. So the spatial metric Q comes in, and so we just use the appropriate measure factor for the scalar field. Turns out we don't need that factor for the momentum, because if it's derived from the Lagrangian density, which has a square root of the term of Q factor, the momentum inherits the same factor, so we don't have to include this in the measure. So we use a different kind of smearing here, and it's still a well-defined Poisson bracket, but also the correct smearing function on the right hand, or the correct measure on the right-hand side. So that can be done. In practice, people don't actually do this when they set up quantum field theories, but especially on flat space-time. But usually you would use Fourier modes and quantize them, and they are also a three-dimensional integration in the canonical version. So It's just a slightly different choice of these smearing functions. And something like this could be done on curved spacetime. But now if we want to quantize gravity as well, then these q's are no longer just functions which we can use in a measure, but they should also become operators. So we should not use these combinations because this would then be a very complicated nonlinear combinations of our quantized variables. Again, for a scalar field that's easy, we can actually, here we smeared it too much. We can just remove the phi smearing, which required the metric here. And there's still one integration here for the momentum. So on the right-hand side, the delta function is integrated out, and it is still finite and well-defined. So one can quantize this expression for a scalar field, but then for tensor fields, which is what we need for gravity itself, there's no simple version like this. Now, the major insight which allowed people to develop loop quantum gravity was that there is a choice of variables, which is not the standard one, canonically, not just the spatial metric and extrinsic curvature, but a densitized triad instead of the metric, so that a relationship here of this form. And the Ashnikova-Barrow connection instead of extrinsic curvature. So there's Ki is basically extrinsic curvature with some factors of the densitized triad and the metric. And gamma is the spin connection, which is gives you a zero covariant derivative of the densitized triad. So just the analog of the Christoffel connection, which you would have for the metric. So that's a connection. So and K is a tensor. So A also is a connection. This little gamma is the Barrow immunity parameter, which I used at some point. I guess even today we don't really need this, so we can set it equal to 1. Classically, there's always a coordinate, a canonical transformation which can change it, so the value doesn't matter. But it turns out after quantization it does, so these canonical transformations are not unitarily implemented. But we don't have to use that ambiguity here. So now these two fields are also canonical, lots of deltas with the same problem for fields. But here, with these new transformation properties of these tensors and connection, we can integrate like this, so we don't use three-dimensional integrations, but for the connection, it's a little bit like a one form, so it has a natural one-dimensional integration along curves. And then since it's a connection, it's not just a one form, it's better to exponentiate it and also multiply it with Pauli matrices here to get rid of some of the indices. E dot is the tangent vector of the curve. So that is just the holonomy, so it's just in terms of these actual fields, that's how it's defined. So it tells you how you can parallel transport a vector field which has an I index here. Or if after multiplying with Pauli matrices an SU2 vector field. So that here we have a one-dimensional integration, and then for a densitized triad, we can integrate it over a two-dimensional surface. So it's a vector field. It's densitized, which means it has one of these square root of the determinant of Q factors. So there's some kind of measure factor included. And if we contract this with the conormal of the spatial surface, and also F is just some smearing function for the remaining index, then we don't need any additional measure factor. We don't have to refer to the metric to make this integration coordinate independent. And so we have a one-dimensional and a two-dimensional integration, which is sufficient to remove delta functions in the Poisson brackets of H and F. So that's how one can construct a representation on a Hilbert space, which is well defined. So one thing here, note that the normal of a surface would usually require a metric, because the normal direction depends on the geometry. But what we need here is just the co-normal. So it's a covariant version, and the way to compute it, if we have, for instance, if the surface is determined like this, so that's our surface. So there's some function in space, and that's constant on the surface. Then co-normal is just equal to dg. So it doesn't require a metric. If we actually wanted the usual normal as a vector field, we would use the spatial metric. But that's not required for the co-normal. So these expressions, at least these f's here, so they're called fluxes. It's a little bit like an electric flux. These are linear in one half of the canonical variables, and holonomies are not linear but exponentiated. So if you work out the Poisson brackets, you still have a linear relationship of this form. So the Poisson bracket of the holonomy with the flux is proportional to the holonomy because the exponential function is then reproduced. It's not the canonical structure, not the canonical bracket, but still a linear algebra. And so it's, and if the curve and the surface don't intersect there, it's just equal to 0. So then they're independent. So I won't go through the full construction, but there's an extra index here which corresponds to possible rotations of the triad. So the triad is just a triple of vectors, which is or vector fields everywhere in space, which is orthogonal and normalized. So that's a way to determine the geometry. It's equivalent to having a metric. But a triad, if you have this triple of vectors, you can just rotate it. So there's an extra symmetry which corresponds to SO3 classically, or maybe SU2 if it's quantized, and that's where the Pauli matrices come in. So there's an extra, on top of Gordon changes, or the diffeomorphism and Hamiltonian constraint, there's an extra rotational symmetry, which also implies a constraint, but it's very simple. It's like a Gauss constraint in electrodynamics, just an SU2 version. So that can usually be solved very easily. Now, the SU2 construction, so the holonomies take values in SU2 after exponentiating here. So there will be SU2 operators, and F is canonically conjugate. They will be like angular momentum operators or derivatives on SU2. And in principle, that's straightforward. We know how to work with angular momenta, but if you have many different operators like this, then you get into these Clebsch-Gordon things and couplings, and it's not always easy to compute an angular momentum spectrum, for instance. So I won't go through this here. It's possible, but in the U1 case, if you just assume we have just like a single vector field instead of the triple, then we still have some additional gauge freedom, but it's just U1, so it's much easier to compute derivatives instead of angular momenta. So in this case, we also just exponentiate the integrated connection or vector potential, so that could be quantized electromagnetism. It's not QED, but it would be a background-independent quantization. So we could couple this to gravity. And then, as I indicated on Monday, we use these operators as some kind of ladder operators, so we use them to excite states, starting with the state which is just a constant on the space of connections. And excited states are then obtained by just multiplying with a bunch of these holonomies for a selection of curves, and maybe taking different powers of each of them. So these are just exponential factors, so we can actually just multiply them, and that's our wave function. And so we illustrate this by just drawing lines for each curve that we used, and we actually use different Ks, then there would be an additional label or maybe a color on each of these edges of the graph. And so for an actual SU2, we call this a spin network state. So people usually try to interpret this in a direct physical way as some kind of discreteness of space, and it is related, but then mathematically it's just a choice of a basis in a Hilbert space. So it's not, in some cases that might be an actual eigenstate of maybe in one of the flux operators, but if we do cosmology, then we shouldn't really have an eigenstate of the spatial areas, for instance. It should be, maybe it should be a coherent state where both the expansion rate or extensor curvature and the geometry are kind of spread out. So that would be a superposition of spin network states, and then it's more difficult to interpret this, but there's still discreteness in the sense that the quantized fluxes on these states have discrete spectra. So in this sense we have like an atomic system, and that's the analog with matter systems. So the flux spectrum is analogous to the harmonic oscillator energy calculation. So we have a commutator. The flux and the holonomy is proportional to the holonomy. So that's similar to the energy of the harmonic oscillator with a raising operator. So we can use the same arguments to derive the flux spectrum, and if we know one eigenstate, then all the others will just be obtained by adding integer multiples of c times the Planck length square. The c is just a numerical factor with some 8 by g in it. Actually, no, there are no units, but there might be some pi's and other numbers, which are not so important. But in this way, we get the standard spectrum, basically just like harmonic oscillator calculations. But then, of course, here it's a field theory, so we have here that's just one type of excitation for a single curve, and then we can use different curves, but it's still integer space, so it doesn't fill it up in a continuous way. And each eigenstate is normalizable, so it's really a discrete spectrum. Now, so these are operators which one can use to analyze the geometry, for instance. So the flux is not exactly the area, but it's closely related, so the area would have a discrete spectrum. The volume is also a more complicated function of the e's, also has a discrete spectrum. But then for the dynamics, we also need the connection, or extrinsic curvature in the Hamiltonian constraint. And that's more difficult because what we've constructed is, so far, it's an exponentiated version of A. And sometimes, well, there's no strict logarithm for operators, so that's we can't really just simply go back to the A's. And in quantum mechanics, if you exponentiate an operator, sometimes you can take a derivative and rewrite the operator. So if you have something like e to the a real number times an operator, like the Hamiltonian, e to the IT Hamiltonian over h bar, you can just take a t derivative and you get the Hamiltonian. But these operators are they're not even continuous in the analog of t. So we can, something that we could do is we could just use a family of curves which get shorter and shorter and approach a point. So that's a little bit like this, a single real number. And we could try to take a derivative by the length of the curve. And if that derivative exists, we have an A operator. But it doesn't exist, and I'm a little dense here, but these are the arguments. So if we try to make an infinitesimal version of holonomies, then we have to check the operator topology. So one way to define this, the different versions, is by just considering expectation values of this family of operators. And these are functions, so we can analyze continuity or differentiability more easily. Now, since these holonomies appear as raising operators, these expectation values are always zero if E is extended. Because there's these, the original state psi and HE psi are both eigenstates of some flux operator according to this calculation with two different eigenvalues. And the flux operators are self-adjoint. And so we know from quantum mechanics, these two states are orthogonal, psi and HE psi. So these expectation values are equal to zero, but if E approaches a single point, we have just psi, which is equal to 1 because of normalization. So this function is not continuous, and that means the operator itself is not differentiable. So the A operator just doesn't exist on the Hilbert space. So we can only quantize something in which the original A in the classical expression has been replaced by an exponential function. And that's why we have to modify the geometry. So that's the simple contribution to the Hamiltonian constraint, and other contribution, they're more complicated, but they have the same features basically. So we use the Yang-Mills curvature of the Ashtika connection and a non-polynomial function of the densitized triads. So classically, it's quadratic in the A's. It's non-polynomial in E, but quadratic in A. But we need exponential functions to use our holonomy operators. So that requires something which is sometimes called regularization and sometimes modification, because if it's regularization, then so that's a more general procedure. So it happens quite often that you have operators which don't exactly match the behavior of your classical expressions. So you would have to modify the classical functions or the theory. So an infrared regulator, for instance, would just impose different boundary conditions. So we are not really modifying the energy, but the solution space by using different boundary conditions. And then we should, after doing some calculations, we should remove the regulator. So letting the volume go back to infinity and allow for all possible solutions. Now here we are actually modifying the energy expression because the A dependence has to be turned into something that's exponential. And then in some cases it's possible to remove the regulator after doing some quantum calculations. In other cases, including loop quantum cosmology, that's not possible. So it is really a modification, not just a regularization, and then we have to be more careful and make sure that's actually physically still well defined. So we jump down here first. One of the conditions of something that's well defined here is covariance or Poincare symmetries in the local picture. And there's one interesting paper here by a string theorist, but it was still addressing some questions in loop quantum gravity, and it's very instructive. So if you just modify these expressions and don't analyze covariance, then basically anything can happen. So we shouldn't really be too proud of finiteness statements, for instance, unless we can show that there's really well-defined covariant and other consistency conditions satisfied. So, and that's still an open question for loop quantum gravity. So I talked about this a little bit more yesterday. These, if we use exponential functions, we can think of them as a power series. So we can start with the classical behavior and add higher orders, higher powers of A, which is a little bit like what we expect for higher curvature terms, but it's not the same because we add only spatial curvature components. So A is a combination of intrinsic and extrinsic curvature tensors. And there's no reason, if we just choose an arbitrary extension to an exponential function, there's no reason why they should be combined to something that's actually space-time covariant. And we're also missing higher time derivatives, so that's something which we would get if it's actually higher curvature. And so that's a question which leads to the quantum space-time results. And then something else here, which it won't be so important, but there's also something which is more like a regularization actually, but we have to divide by a function of E which certainly can be zero. And after quantization, we would have to use the flux operator for E, which has a discrete spectrum containing zero. So it does not have a densely defined inverse. We cannot, even though we didn't exponentiate the E's, we cannot directly turn this expression into an operator. But there is a way which is actually not as strongly modified as the holonomy modification, which one can use. So it is not as important as understanding these holonomies. So so let's get the main features of loop quantum gravity, which leads us to these modifications. And then in loop quantum cosmology, one just tries to copy the same substitution. So also here the Friedmann equation is just quadratic, and the only remaining component of this Ashoka connection. And we use a combination of exponential functions, like this one. It's not unique, but that's one possibility, and insert it in here. So that's the modified Friedmann equation. And if we just use it, we get something like a balance, or at least bounded energy densities, because the left-hand side is bounded, so rho also has to be bounded. In this context, one can at least analyze these expansions. So now we can, instead of just using that full function, we can see if there's really a meaningful asymptotic expansion. So the first order correction would be like this, so it would be some density over Planck density correction, but there will also be higher order terms. Now to see implications, derive other potentially physical effects, it's useful to reformulate the equation, and that's called an effective Riemann equation. It's not the same kind of effective that I was talking about in the last few lectures. It doesn't bring in quantum fluctuations, but it reformulates this equation into something which looks nicer for a cosmologist. So we start with this expression here, and use this relationship. So P is just A squared, so that's an identity which we always have. And we can compute this P dot here using a canonical equation of motion for the modified Hamiltonian. So it's derivative, so another sine function here. And now we can solve this expression for the sine squared of C, which we have up here. So it's not the same, there's an extra factor of 2, so we have to use some trig identities. But well, it's possible to invert these relationships and replace the C dependence by dependence on P dot or A dot. And if we insert this up here, then we just get the standard quadratic Hubble parameter on the left-hand side, and the classical term minus another energy contribution. So that's the effective Riemann equation. And there are no, if we just stop the expression, there are no further approximations. So initially we have a power series in C, but the final result stops at the quadratic term in both. So we're not ignoring higher order terms, they just completely cancel out in these identities. And that's another way to see the bounds in these models. So it's now possible for the right-hand side to be 0 at some density which has this form. So it's about the Planck density if L is the Planck length. And if that's 0, then A dot is equal to 0. So we can have a minimum in the evolution of the scale factor. It's not just bounded density, it's also where the scale factor bounces back. One can also compute the second order derivative and make sure it's actually a minimum, not a maximum at the turning point. So I don't think I included the plot, but you've probably seen this wave function, seen on some of these posters, which shows the bounds after quantization. Now, it turns out, so that's a nice equation which cosmologists usually like. So there's, you can just, for instance, use perturbative inhomogeneity with a background which is modified in this form. But in terms of the derivation is quite tricky, and so to see this, we can actually take this sine function more seriously as a curvature expansion. So if we don't use the full sine function, but only the next term on which would correct the classical expression, which is now quartic in C. We follow the same procedure, so we use the relation between A dot and P dot, and now this equation for P dot based on this H1. And we can also invert this, compute C perturbatively in terms of P dot inserted, and we get exactly the same effective equation. It's also quadratic. So it doesn't matter, we can just use the next order correction or the full expansion and we get the same effective Riemann equation. Now we go to one order higher here, so up to C to the fourth, it is no longer the same, which means that if we would just have a perturbative expansion, if we would have to go through order by order in this C expansion here, then initially we would see lots of complicated terms, higher powers of rho. But eventually, if we go back to the full sine function, for some reason all these higher order terms cancel out. Which is nice, of course, in this model, but it's also dangerous because if you just slightly modify the system, if you maybe even spatial curvature, a spatial curvature term, or anisotropy, or actual quantum corrections, fluctuations, would probably lead to different modifications of each of these terms, and you won't have these cancellations anymore. So that's why there's still a question of whether the results, like the bounds, actually survive if we include additional quantum effects. And yeah, here's a little bit more about the quantization. So we if we want to test quantum effects, we need a Hilbert space or some kind of quantization. So just a few mathematical details on this slide. So in this isotropic model, again, there's just one connection component C. And if we want to follow the loop quantization, we should exponentiate it. And it can be represented on a Hilbert space, which is not the standard big L2, but the space of sequences. But not over the integers, but over the real line, basically,